Welcome to another video on understanding large language models. Up until now, we have discussed how these models work, followed by videos on datasets and tokenization. Then we explored embeddings, and in the most recent video, we covered the attention mechanism. If you've watched all these, you should now have a solid understanding of how an LLM processes and represents information at different stages. In this video, we will focus on how these models are trained to generate text. We will break this down into three key aspects: model architecture, computational resources, and what it takes to train deep learning models of this scale. Let's start by looking at the architecture of GPT-2 Small. This model has an embedding dimension of 768, a context size of 1024, 12 decoder layers, 12 attention heads, and a total vocabulary size of 50,257. First, let's start by counting the total number of parameters in this model. The embedding layer contains a learned embedding matrix, which is trained during model training. This layer alone has approximately 38 million parameters. Next, we have positional encoding, which helps the model understand word order. This can either be a fixed function or a trainable layer. In this case, we assume it is trainable, contributing about 0.8 million parameters. Then comes the attention block, which consists of the query, key, and value matrices, all of which are trainable. Additionally, multi-head attention includes an output projection layer. Together, a single multi-head attention layer contains around 2.3 million parameters. The feed-forward layer consists of approximately 4.7 million parameters. Here, we are ignoring bias and normalization parameters since they contribute only a few thousand parameters, which is negligible in comparison. Repeating this structure across 12 layers results in approximately 85 million parameters. After that, we have the final linear layer, but since this layer shares parameters with the embedding layer, we do not count them separately. Summing up all these components, the GPT-2 Small model has a total of around 124 million parameters. However, this is considered a small model compared to modern large-scale LLMs, which now contain billions or even trillions of parameters. These larger models have deeper architectures with more trainable layers, larger model dimensions, and additional repetitions, making them significantly more powerful. Now let's talk about the dataset. These models are trained on large datasets containing billions or even trillions of tokens. To prepare the training data, we take a fixed context size and batch size. For example, if we take a context size of 10 and a batch size of 2, the training data and its labels are structured by shifting the tokens one step ahead for the labels. This process happens after tokenization, ensuring that each training example contains the exact number of tokens needed. In traditional machine learning, you might have seen models trained for multiple epochs, meaning the entire dataset is passed through the model multiple times. This helps improve learning by allowing the model to see the same data repeatedly and adjust its parameters accordingly. However, when training large language models, we do not usually count epochs. Instead, we use what is called training steps. This is because the datasets are massive, often in the range of billions or trillions of tokens, making it infeasible and unnecessary to repeat the same training examples multiple times. In most cases, each training example is used only once. For example, if we have a total training dataset size of 50 million tokens, and we set a context size of 1024 with a batch size of 32, then each training step processes 32 sequences of 1024 tokens. To compute the total number of training steps required for one full pass through the dataset, we divide 50 million tokens by the total tokens processed in one step 1024 times 32, which gives us approximately 1526 training steps. In real-world pretraining, 50 million tokens is a very small dataset. Typically, pretraining involves datasets with trillions of tokens, meaning the total number of training steps would be in the thousands or even more. In research papers and reports, you will often see statements like Model X trained on Y amount of tokens, which refers to the total number of tokens processed during training. Now let's talk about the memory requirements needed to train these models. Let's consider a model with 1 billion parameters using full precision floating point representation, 32-bit, to store each parameter. Just to store the model weights, we would need around 4 GB of memory. However, this is only for loading the model weights, and actual training requires much more memory. The first thing that needs to be stored is the model weights. In addition, each neuron produces an output activation when given an input, and these activations must be stored in memory. During backpropagation, gradients are computed and also need to be stored. If we are using an optimizer like Atom, which is commonly used in large language models, we also need to store the optimizer state in memory. This is crucial for efficient training. The memory requirement for gradients is the same as the model parameters since each parameter has both a weight value and a gradient value. Additionally, Atom requires storing 2 extra values for each parameter, meaning we need double the size of the model weight to store the optimizer state. On top of this, we need to account for activation memory. During training, each neuron produces output activations, and the total memory required depends on batch size, context size, and the number of layers in the model. More input tokens mean more activations, so roughly, activation memory can take around 10 to 15 GB in our case. Many people may not consider activation memory, and even if everything looks fine during model loading, they might run into a CUDA out-of-memory error when training starts. Considering all these factors, training a 1 billion parameter model using full precision floating point requires around 30 GB of memory. However, today's large language models contain hundreds of billions of parameters, which require significantly more computational resources. For training large models, high-performance GPUs are needed. One of the most popular GPUs for training LLMs is the H100, which has 80 GB of memory. A single GPU can handle smaller models of around 1 billion parameters, but for training models with billions of parameters, multiple GPUs must work together to train a single model efficiently. This requires GPU parallelism. One approach is data parallelism, where multiple GPUs are used to speed up training. In this method, each GPU contains a full copy of the model, and the training batch is split into smaller microbatches across GPUs. After processing, the gradients are synchronized across all GPUs to update the model weights. However, this approach does not solve the problem of large model sizes. It is mainly used for speeding up training. In data parallelism, the full model must fit within a single GPU's memory. To handle large models that cannot fit in a single GPU, we use model parallelism. One type of model parallelism is pipeline parallelism, where different model layers are distributed across multiple GPUs. Each GPU processes a portion of the model and passes the activations to the next GPU in the pipeline. However, this approach leads to inefficient GPU utilization, since each GPU has to wait for the previous one to finish before starting its computation. Some techniques improve this, but overall, pipeline parallelism still results in underutilized GPUs. A more efficient approach is tensor parallelism, where instead of distributing the model layer by layer, we divide individual tensors across multiple GPUs. Instead of a single GPU performing large matrix multiplications, the workload is split among multiple GPUs, and the results are later combined. This allows for better GPU utilization, but it requires frequent communication between GPUs. In practice, multiple parallelism techniques are combined to form hybrid parallelism, which balances efficiency and resource utilization. The goal is to maximize GPU usage while also speeding up training, since training large models can take weeks or even months. There are several strategies for training trillion-parameter models across multiple devices. I have provided links to some useful resources in the description, which you can check for more details. Now let's take a simple training example and process it step by step. Assume we have a training set containing just 5 tokens in a single sequence within a batch. The corresponding labels for this sequence are simply the next tokens in the sequence, shifted by 1 position. We use the same model we defined earlier. When we pass this input sequence into the model, it first goes through the embedding layer, then through the attention mechanism, and finally reaches the feed-forward layer. One thing we didn't mention earlier is the nonlinearity introduced in this layer. After the first layer, a nonlinear activation function is applied. Here, let's take GPU. GPU is an activation function commonly used in transformer-based models like GPT. GPU smoothly approximates activation using a Gaussian distribution. This helps improve gradient flow and overall model performance by allowing a mix of linear and nonlinear activations rather than a hard cutoff. Now, as the tokens pass through multiple layers, they eventually reach the final linear layer. At this stage, the model outputs logits of size equal to the vocabulary size for each of the 5 tokens in our example. Applying softmax to these logits gives a probability distribution over the vocabulary for each token position. Since we now have the correct next token labels, we need to compute how well the model predicts them. For this, we use cross-entropy. Cross-entropy is a commonly used loss function in classification problems. For example, if we are classifying into 4 possible classes, we get probability distribution over 4 classes. We encode the correct class using one-hot encoding, where all positions are set to 0 except for the correct class, which is set to 1. In this case, cross-entropy is computed by taking the predicted probability of the correct class and calculating the negative log likelihood. This loss function is called categorical cross-entropy and is used in multi-class classification problem in machine learning. Here, since all other values in the label are 0 and only the correct label probability is used to compute cross-entropy, we can just take the training label as the correct index position and then compute the cross-entropy, which gives the same output. By doing this, we save a lot of memory and computation for not storing one-hot encoding labels, and also make computation a lot easier. This modification is called sparse categorical cross-entropy, and we use this in large language model to save a lot of memory by not storing those one-hot encoded labels. The key idea behind cross-entropy loss is that it assigns a low loss when the model gives high probability prediction to correct label, and a high loss when the model is uncertain or incorrect. Now that we have both the predicted probability distribution and the correct next token labels in index format, we can now compute the cross-entropy loss across all tokens in the training sequence. Since we are predicting the next token for each token in the sequence, we compute the loss for all 5 tokens in this example. This setup follows the principle of causal language modeling, where the model predicts the next token using only the tokens before it, and in the attention mechanism, we achieve this by masking future tokens, preventing the model from looking ahead during training. For this particular example, we got a loss value of around 4. But how do we interpret whether this loss value is reasonable? Suppose we have a script that simply selects the next token randomly from the vocabulary, assuming all tokens have equal probability of appearing. For a vocabulary size of 50,257, the cross-entropy loss for random selection would be around 11. This gives us some idea about what our loss should be, and when training our model, we should expect the loss to start around this value and gradually decrease as training process continues. If we take a similar model with only 100 tokens in its vocabulary, the expected loss for random selection would be around 5. So after training, achieving a loss of around 3 would be considered good for a large vocabulary model, but not very impressive for a model with only 100 tokens. This was an overview of how cross-entropy is used in training large language models. We now have a proper loss function to evaluate our model's performance, but we need to optimize this error during training. Let's take a classic optimization example where we start with a high loss and want to find the minima, meaning a point where the loss is at its lowest. A lower loss indicates that our model is more confident in predicting the correct next token. To reach the minima, we need to update the model's weights. This is done by decreasing each weight by a small amount in the direction that reduces the loss. The direction is determined using gradients, which we get by computing the derivative of the loss function with respect to the weight. The derivative tells us how our loss changes as the weight changes. A positive gradient means the loss is increasing as we increase the weight, and the value gives us the idea that by how much it is increasing. Since we want to minimize loss, we move opposite to the gradient's direction and approach to the minima, which means we decrease the error. Now taking the step equal to the gradient value but in the opposite direction, we are reducing the loss value and approaching to the minima. But updating our weight by taking value equal to the gradient value might overshoot the minima and leads to other side which we don't want. So instead of making a huge jump equal to the gradient value, we take small steps, controlled by a hyperparameter called learning rate. This helps the model gradually move closer to the minima as we optimize over time with more training example. So even if we are on the other side, with the help of gradient we can approach to the minima here. This optimization technique is called gradient descent. However, gradient descent has some challenges. First, this algorithm is too sensitive to learning rate. If the learning rate is too large, the model might overshoot and take unstable steps, which is not desirable. If the learning rate is too small, it may take too long to reach the minimum. The optimization landscape is not always a simple curve, but can have multiple local minima. So using a simple gradient descent might not be useful here, where the model can get stuck without reaching the best minima. To address these issues, Atom Optimizer is used in large language models. I don't want to go into detail about how this works, but to give simple intuition, what Atom does is it uses momentum, which helps Atom escape local minima by maintaining a moving average of past gradients and taking careful steps if the slope is too steep. Since Atom requires additional values called as first moment and second moment, we need to store them in memory. For a single parameter, we need to store its weight values, activation values, which depend on how many examples we are processing at a time, gradient values, and optimizer state. Now let's write down what we have taken so far. We use Jello activation in the feed-forward layer. We can also use Swigglue as an alternative. Atom Optimizer is preferred due to its adaptive nature. In practice, a variant called Atom W, which means atom with weight decay, is also commonly used, and batch size is set to 32. However, large batch sizes can be memory-intensive, leading to out-of-memory errors due to increased activation storage. So instead of processing a large batch at once, we can take a smaller batch if we have memory constraint. Let's take a batch size 16 and compute its gradient. Then we backpropagate but do not update the weights yet, and also do not reset it to 0, just store it, and take another small batch and compute its gradient. After accumulating enough gradients to reach the desired batch size, here we do two-step to reach our desired batch size, we average the gradients and update the weights. Gradient accumulation effectively simulates a larger batch size using multiple smaller steps, though it is not exact as using larger batch size but works effectively. Another key hyperparameter is learning rate. So instead of keeping the learning rate constant, we can gradually increase it during the warm-up phase until it reaches the maximum value, and then gradually decrease it over time to ensure stable convergence. We can define different scheduling strategies and choose the number of warm-up steps based on the model and dataset. Finally, an important consideration is saving model checkpoints at regular intervals. This ensures that if an error occurs during training, we can resume from the last saved state instead of restarting from scratch. These are some of the key hyperparameters to consider during training. There are many more, but these are among the most important. Now that we have everything set up, we can finally start the training step. With a properly configured GPU and the correct model setup, we can begin training and expect to see gradual improvements over time. However, training a large language model can take a significant amount of time, depending on factors like model size, where larger models require more computation, dataset size, where more data means longer training time. Another factor is hardware resources and some optimization techniques to train our models smoothly. After training on a massive dataset, we obtain a foundational model, also called a pretrained model or base model. This model has learned general language patterns and can now generate text based on input prompts. For example, if we give the model the prompt, AI stands for, the model generates the most likely next token based on what it has learned. So now the data flows like in the training stage, where first it is tokenized into tokens, and the model computes outputs which are raw logits. Then the softmax activation convert logits into a probability distribution over possible next tokens. However, unlike during training, where we compute loss on all tokens in generation mode, we only care about the last token's probability distribution. This is because we are not training the model, but generating new tokens, so we don't care about what the prior tokens predict. We only care about the last token probabilities, because it has context of all other previous token and also in attention calculation. Only the last token fully benefits from all previous tokens. So in causal language modeling, each token only attends to past tokens, and the last token's output is the only one that includes the full context, making it the best candidate for next token prediction. Once we obtain the last token's probability distribution, we sample a token from it. If the model is well trained, it should predict a reasonable next token. Now the predicted token is added in the context, and then again continue the same process. So looking at the high level, first we tokenize the query, then the model processes the tokens and gives us raw logits. These raw logits then, when applying softmax, gives probability distribution, and by taking the last token probability vector, we can get the token index of the next token. We can then again use the tokenizer to decode the token from its id. Since we already have the generated tokens, we do not retokenize the input. Instead, we simply append the newly predicted token index and continue predicting. Now to continue text generation, the predicted token is added to the input sequence, and the model is run again to predict the next token. This process repeats until we reach the maximum sequence length or another stopping condition. While a base model can generate text, it is not yet optimized for specific tasks like chatbots. For that, we perform fine-tuning. Fine-tuning involves further training the model on a higher quality dataset but smaller than the pretraining dataset, and are formatted with special tokens to make it like human AI chat conversations. Here we are considering full fine-tuning, meaning we train all the layers again. However, you can also explore another type of training that helps fine-tune models with low resources, called parameter-efficient fine-tuning. It is slightly different in how the model is trained, but the goal remains the same, which is causal language modeling, predicting the next token. When using a fine-tuned chatbot model, the input is internally formatted in some kind of prompt template. We don't explicitly do this, but this may differ according to the chat providers. Since the assistant field is empty in the final input sequence, the model will generate the next tokens based on the context. Because of fine-tuning, the response will be well-structured and aligned with the desired chatbot behavior, and we can have a language model that nearly mimics as if real human is behind the chatbot. This completes the training and fine-tuning for a large language model. In both the cases, the core idea remains the same: train a model to predict the most likely next token given the context. Thank you for watching. See you in the next video.